Hi. LCD character displays. Chances are you've seen them used in products for hobbies, often used with Arduinos and other such things for giving a display to your project that you build at home. You don't see them used all that often in professional environments. You don't see it used, for instance, in consumer products that much anymore, although they had been used a bit in the past. I think it's kind of fallen out of favor for TFT displays and some of the more high-end products with a better graphical interface. But still, I don't want to downplay the usefulness that a LCD character display can have, especially for elevating your home product or your homebrew whatever you want to make in general. So I want to talk a little bit today about what character displays are, LCD character displays I should say, what they are, how they work, and we may even go through, look at some code, and custom design a Hello World program for an LCD display. Okay, so let's look at our typical LCD display. Well, I've drawn it here. Again, sorry, my drawing skills aren't the greatest. What we have in the middle here, I tried to draw what the actual display would be. You can see it's outlined in the green or yellow. That's probably the most popular color, the green-yellow, but there's a lot of different colors now. There's orange, there's red, there's blue, white, you name it, there's probably a color for it. But this is probably the original and the most common still. And then we have the black cover. This black cover that you see around it, that you would have seen in the first scene of this video, there's what's called zebra strips under there. And they're just conductive strips on the top and the bottom. And what those do is they actually bring the signals from the LCD display driver up onto the actual LCD glass itself. Anyhow, that's the black metal surround that holds that down. And then out here you have your circuit board that the whole thing rests on. It's not always this big, but I kind of drew it bigger just to show it as an example. Okay, anyhow, there are a lot of different size LCD character displays. It doesn't just come in one standard flavor. In fact, there is a dizzying assortment. This is a common list of some of the more common ones. We've got 1x8, 1x12, 1x16, 2x8, 2x12, 2x16, 2x20, 2x24, 2x40. Well, what do all these mean? Well, first off, the first number in that is the row. So you've got a single row, a dual row, or a 4-row. As far as I know, there's not a 3-row, but I have seen some that are more than 4. But these are the most common, 1, 2, and 4. So that means basically this looks like, based on the size of the letters that I put there, this would probably be a 4-row. 1, 2, 3, 4. And let's see, 1, 2, 3, 4, 5, 6. You count the space. 7, 8, 9, 10, 11, 12, 13, 14. 15, 16, 17, 18, 19, 20. So this would probably be somewhere between, say, a 16 and a 20 as far as columns this way. So the first number is the row, the second number is the number of columns. Okay, so this kind of dictates the maximum number of characters that you can fit on any given screen. If you know that you only need a few, say a single line, just maybe all you needed it to say was hello, or maybe just display a number, well, a 1x8 might be good enough for you because it's less expensive and it's just generally easier to drive and work with. The only exception to all of these, I should say with the exception of one, all of these are driven by a single LCD display driver. Like anything else, there's more than one type. Sorry, forgot to write it down here. I had to stop the video. But the most common one is the Hitachi HD 4470. That's been around for decades, and it is by far still the most common LCD display driver. Any of the other types that are out there, ST has one, there's a couple other I've seen, they very closely match this one anyway. So if you get to know the Hitachi chipset, you're probably going to be in good enough shape to know all of them. Okay, so I want to go through the different pins that a typical LCD character display will have. They'll vary somewhat, but in general they'll be very close to this layout. So, actually I should say it's more or less standardized. I would say that most character displays do follow this pinout, and it would be the exception to the rule when it's different. So what do we have here? And hopefully you can see this, it's a little bit small. Okay, we have VSS, essentially ground or common. VDD, that's going to be your +5 or 3.3 volts. 5 volts is still the most common, but there's certainly 3.3 volts out there. And there may be other voltages as well. But 3.3, 5, most common. VO, that's your contrast pin. And normally what you would do is take, say, a 10 kilo ohm potentiometer, tie it between VSS, VDD, and your wiper would go to VO. I'll show a completed schematic with more of this later, and it'll become clearer. RS, that's your register select. We'll go into that more. Read-write, well that's obvious. Either you're reading from this or you're writing to it. Typically you're going to be writing to this. It's not very often that you're going to be reading. In fact, the only real reason that typical applications need to read is to read the busy flag to see if it's processing anything, so that it waits before it sends the next instruction. In a lot of instances, you don't have to worry about this, and you can simply tie it, I can't remember if it's high or to ground, but one of those, and it will make it a write-only device, which is what I typically do, just to make it simpler, and to not use an extra pin on your microcontroller if you don't have to. E is for enable, that's the enable pin. It does more than simply enable this device. Yes, true, without that high it won't be enabled. Or is it low? I don't remember, I'll have to look. But yeah, enable does a lot more. You actually have to flash, I believe it's high, or maybe it was low, high, I don't remember. But you flash it on and off, and that actually will latch the data into the controller. I know it's sounding complicated, but once you see the flow chart and get the information, it won't be as bad as it sounds. Okay, D0 through D7. We can actually cover this all in one fall swoop, because what is D0 through D7? Well, it's 1 byte, and that is not an accident. The reason it's 1 byte is because you're either sending a command, byte by byte, or you're sending an ASCII character to the display, which happens to be 8 bits. So this D0 through D7, critical. That's how you actually send your data to the LCD display. And then LED plus and minus, that's optional, it's not on all of them. That's for LCD displays that actually have a backlight on them. Most, I think, these days probably do, but there are some that don't. We have reflective and transflective displays that don't need the backlight. I'm sorry, I have once again failed to provide you with proper screen capture. I hope this is in focus and this is relatively easy to read. I can see myself. Hi. Anyhow, hopefully this will be good enough and you can see this in HD. What we have here is a schematic with our LCD display up here in the top right, and we have a PIC 16F690 microcontroller. It doesn't really matter which one you use. You can use it with certainly a lot more things other than PICs, but this happens to be a project that I did in the past and I used a PIC. So you can kind of ignore this over here. That's for your in-circuit serial programming. What we really want to concentrate on is the wiring to our LCD display. And you'll notice that there really isn't all that complicated of wiring. For the most part, there's only 1, 2 passives, and everything else goes to GPIO pins on the microcontroller. So let's take a close-up look here, if I may zoom in on our LCD. You can see that our ground is wired right down here to ground. Our VCC goes here to 5 volts, as one would expect, and of course you have a bypass capacitor there, 0.1 microfarads. You'd want to use a good tantalum or ceramic type and try to get that as close to the actual LCD display as possible, just like you would do with any other type of logic chip. Okay, now we come to our contrast pin, or what we called VO before. It goes by different names, but it's the same thing, and it's still the third pin in. So that comes down to here. I'm sorry, here. Can't see that. Real good blogging abilities here, huh? Wow. Now you can see that. There we go. Oh, man. Okay. So your contrast pin comes down to the wiper here on the potentiometer. It's got a little weird leg on there. I don't like that. I don't remember doing that, but apparently I did. Anyhow, contrast pin goes to the wiper of the pot, 10K like I mentioned before. One end goes to your 5-volt supply up here. The other end goes down to ground, just as I mentioned before. So a pot with either end going to 5 volts and ground, the wiper goes to your contrast pin. Basically all that does is adjust the contrast on your display to make it darker or lighter to your preference, or sometimes you actually need to adjust the contrast depending on the viewing angle. If you're viewing the LCD display from an extreme angle, either looking up at it or downward at it, then it often helps to adjust the contrast to make it easier to read from one of those angles. Okay, so I'm going to zoom out. Hopefully you can see this here. We have our register select pin, which is next, just as we mentioned on the whiteboard earlier. Register select comes over here to a regular GPIO pin. Same thing with your enable over here. Now you notice I skipped read write. That's because the read write actually gets pulled down low to ground. And what that does is this permanently keeps this chip as a write only. You can only write to the, I keep saying chip, you can only write to the character display. Now you don't have to do that. You could tie your read-write pin to one of your GPIO pins on your microcontroller and control whether you read or write to it, but it is much simpler if you simply tie that to ground. Okay, so D0 through D7, these are your data pins. This is where your actual ASCII character display data comes through. Down and to, I would recommend, since there's 8 of them, to simply go to one port on your microcontroller. Now given not every microcontroller has a port with 8 bits in it, but typical 8-bit microcontrollers have at least one port that has an 8-bit output, or GPIO I should say, on it. So, you know, it's not too bad. And then up here you can see I left our LED disconnected because this particular display did not have a backlight. I feel a bit remiss in failing to point out that there are multiple ways, not just one way, to configure your LCD character display. And I know you're looking over here and you're saying, what the? Andrew, you didn't connect all the pins. I know, you don't have to. On microcontrollers where pin count is at a premium, you can actually drive the LCD character display with just 4 bits. And I know you're thinking again, well, geez, if I can run it on 4 bits, why don't I just do that all the time? Easy, done. Well, it's not quite so simple. It's much more complicated in software to try and run it on 4 bits because you actually still have to send the 8-bit ASCII data, but now you need to send half of an ASCII character, shift it over 4 bits, and then send the other half while masking either end, you know, whether it be the most significant 4 or the least significant 4 as you're sending it over. So now it also literally takes twice as long because now you're only sending half the amount of data at a time. So for applications where you need it to update quickly, that wouldn't be a very good option. It also, like I said, really complicates the software. So it's not terribly complicated. Once you've set up the LCD display driving program, it pretty much just does it and you call it as needed. But it is a little bit more work up front. But like I said, this is a good option for when you only have a few pins available on your microcontroller. Okay, so now we've seen how an LCD display works, well, how it's connected I should say. Well, what's the procedure for getting this thing going? Well, I want to start out by saying this is the LCD procedure. Number one, we need to wait. We need to wait for that LCD character display to kind of power up and go through its initialization process internally. So we need to wait more than 15 milliseconds after we power up our microcontroller. And we'll basically just put a wait loop inside the micro as we're doing the initialization procedure. So we'll wait for more than 15 milliseconds. I often go all the way up to 100 milliseconds just to ensure stability. This is kind of an absolute minimum. Maybe 100 is kind of too long. 50 milliseconds would probably be enough because 100 milliseconds is long enough that you can kind of feel that wait time. Okay, so number two, send command that's 0x30. What does that mean? Well, if you're not familiar with C programming, that 0x just indicates that that's a hexadecimal number. So that's hexadecimal 30. We want to send it on the data lines, that's D0 through D7, on the microcontroller to the LCD display. What does that do? Well, essentially it's telling the LCD display to wake up. We waited for that period of time and now we're saying, okay, well, you had time to get your initialization done, now you need to wake up. So we send this command, and what we do is we actually, now, I'm getting ahead of myself here. There is a fundamental difference between sending a command and sending data to the LCD display. When you send a command, you're still sending the 8 data bits, but those 8 data bits represent something that you're telling the display to do. For example, to initialize, to set the cursor on, to shift the display, any number of things. There's actually a list to that I can show you that are commands that tell the LCD display what to do. As you're initializing the LCD display, you're sending entirely commands. So we want to send a command. Now, in order to send a command, we want to tie the register, not tie, I shouldn't say, we want to pull the register select pin low with our microcontroller during the duration of this. And then in order to send the command, we put the data on the port, and then we flash the enable pin from high to low. Remember how I said we need to clock in the data with the enable pin? It's not simply just an enable pin. So yeah, we want to go high to low to clock in that data. Okay, so we send command 0x30, wait more than 5 milliseconds, do it again, now wait greater than 160 microseconds, really getting quicker there. We do it a third time, we wait more than 160 microseconds. Why do we do it 3 times? Wouldn't 1 be enough? You would think so, but it's a little groggy and you have to kind of coax it to wake up. After the 3rd time, it gets the hint that you're telling it to reset itself and to finish its initialization. So by this point, it should have reset itself, it should be initialized, and now you just need to start sending the commands to set the LCD display up for the type of use that you want to give it. So by step 5, we're telling it, do we want it to be a 1 or 2 line? That's the rows. Do we want 1 row or 2 row? Well, this is kind of confusing because earlier I showed you that they have 4 row displays. So why is it 1 or 2? Wouldn't there be more options than that? Well, unfortunately not. The Hitachi chipset is set up such that it's made to drive 1 or 2 line displays. It actually can't drive a 4-line display. Well, then how does it work? Well, the answer is, and it's a little confusing, this is one of the really confusing and irritating aspects about LCD character displays. It can only display the first, say, 20 characters, and then, well, you know what, I think it's time for an example. Let's just talk about how here we want to set 4-bit or 8-bit. I'm going to come back to it. We want to set either 4-bit or 8-bit like we talked about. Do we want the cursor on or not? Generally, you probably don't. Turn the display on and start sending your data. Well, let's look at these commands a little bit closer because I think just looking at it in this format is a little bit confusing. But here it is. So hopefully you can reference back to this, pause the video, and go through and understand the procedure a little bit better. Okay, let's say for instance we have a 4x20 LCD display. So in this instance we would want to set our display to a 2-line mode. And here's why, and this is again one of the really irritating things about LCD displays. It would seem that you could just type your 20 characters into that top line, and then as soon as you get to 20, it'll return right back to line 2. You do another 20 characters, it returns to line 3, and so on. No, that's not how it works. That'd be too easy. What it actually does is the chipset is always designed to display 40 characters. So it's going to do 1 through 20 just fine. But then if you were to type in another character, it's going to go here, and then so on through the next 20 off the display. It won't even show it until you get all the way through the 40. Then you would think, well, okay, well then it's going to come back to line 2 after that, right? No! It goes 1 through 20, the next 40, and then it goes down to line 3. Yeah. Then you do 1 through 20 there, go out through your 40, and then you're thinking, well, it's got to go to 4 now, right? No. So it goes through all that, and then it comes up to 2. And then it goes 2 through 40, and well, there's only 1 line left, then it finally comes down to 4. So 1 out to here, 3 out to here, 2 out to here, 4 out to here. Wow, that's annoying. Well, the issue is it was never really designed for this type of display. So unless you truly have a 1 or a 2-line display, it's going to do strange things like that because it's always designed to drive 2 lines at 40 characters. If you have a 2-line 40 character, that's perfect. It'll work just fine. So anyway, that's one of the weird things. If you have a 4-line character display, you actually want to set it up for 2 lines. Okay, so we've come to a point where I think it might actually be easier to just look at the code. And for any of you that don't understand C code, you can see to the right here where I have the dual forward slashes. That's a comment to the right there. So these comments describe what each line is actually doing. So we start our C program with our normal includes, standard I/O, standard library. One thing, if you're wanting to drive a LCD character display, you also need to include string.h in order for this to work correctly. And of course there's our header file for our PIC16F690. I've declared some of our information there. This void set defaults just sets our I/O for our GPIO pins, and it tells it to use the primary internal oscillator at 8 MHz. Here we have delay milliseconds, which, sorry about that. My lab assistant doesn't know when it's inappropriate to bark. You would think by now he would know. Anyhow, we have delay milliseconds, which is a loop that makes a millisecond delay. Here I've defined the 2 pins, the enable pin and the register select pin, just so that I can type LCD enable and LCD register select instead of having to type all of the port information every time. Okay, now we're getting to the interesting stuff. Here you can see I have a subroutine for, see, I'm making that go out of focus every time. Here we have a subroutine for sending a command. First, at the top, we put the data on the LCD port. So that's the 8 bits of data that we want to send as a command. Next, we set our register select to low, which tells the LCD display that we're sending a command, or an instruction, if you will. And then, what we do, remember I said we flash that enable pin? Here, we set the enable pin high, wait 1 millisecond, and then set it low. That clocks in that command to tell the display that's what we want to do. Then we just wait 10 milliseconds before returning from this, just for good measure to make sure that everything went in. 10 milliseconds is actually kind of long, but in this instance I wanted it to be really robust. And you'll notice that the right, oh sorry, I just kicked the tripod there. You notice that the right subroutine is very similar. It's almost the same thing. We put the data on the port, except something's different here. The register select, instead of being the 0 that we had to tell it that we're sending a command, now we're setting that to 1 to tell it that we're sending word data, that we're sending ASCII data. So that's how it knows the difference. Then we still do our clock where we set the enable high, wait 1 millisecond, and then set it low, and then we wait our 10 milliseconds. Everything else is the same, except, yeah, you'll see here, extra register select required for some strange reason. Never figured that out. I don't know why. It should be so simple, but for some reason that doesn't work correctly on this particular chip. It works in other chips, but for some reason I have to add that there, and I don't know why. Anyhow, ignore that line. That wouldn't normally be there. We would just do our enable high, wait 1 millisecond, set our enable low, and then wait our 10 milliseconds. Okay. So the very first thing that we're going to do is actually initialize the LCD display. So when we do our initialization routine, and again, this is the very first thing that we do, and you'll see down here in our main, we set our defaults for the microcontroller, but then the next thing that we do is we initialize the LCD. This actually calls this subroutine up here. So we're waiting 100 milliseconds, way longer than what you really need to wait. Remember I said it's 15 milliseconds minimum. I just wanted this to be really robust, and 100 milliseconds at power up didn't really matter for this application, so I just left it at the 100. You can do a lot less if you'd like, and feel free to try it. Keep minimizing that until you get to a point where it's unstable. Play with it. I always encourage people to play with these things and see what happens when you try something. That's what electronics is all about. Anyhow, the next line, you can see that we're calling that subroutine command, and we're sending this data, this 8 bits of data. So now let me point out, because some eagle-eyed viewers will notice this, I don't have my wake up routines in here where I send the hex 30. In this particular instance, for whatever reason, I was playing with it. It worked without those. So I just left it. I could have put them in there, but it worked without it, so I didn't bother doing it. You probably will want to. If this is being done for anything that needs any kind of reliability at all, well, you're going to want to do that. And certainly you don't want to come down the line later and it's not working and you're chasing your tail trying to figure out, why the hell doesn't this thing work? Well, probably because you skipped that. So yeah, just because I do it, don't do it. I should lead by example, I guess. But anyway, yeah, it's not in there. Normally what you would do is you'd have your 100 millisecond delay, wake up, wait, wake up, wait, wake up, wait, and then you'd send your command to tell it whether or not it's 8-bit or 4-bit, or it's a 1-line or 2-line. In this instance, we're doing a 8-bit 2-line display. Okay, so then the next command we send is to set the cursor. Then the command to tell the display to come on. The cursor's on. That set cursor basically is it blinking? Is it the full cursor, or is it just the bar at the bottom? That sort of thing. And it also sets whether or not the display shifts every time you enter a character. Be careful with the display shift. It may not be what you think it is, but feel free to play with it. What it does is, every time you write a letter, it shifts the entire display, not just the cursor. So that's probably not what you were expecting it to be. But try it. Trust me, it'll be fun. And then entry mode set, that's just telling it to turn the display on and that you're ready to display data. And command 80, you'll find that in the command table for the chipset. What that does is it puts the cursor at the top left, basically what I would call the home position. Alright, finally, after all of that initialization, we're ready to put some data on the screen. The way we do that, or the way that I've done this, you could just simply put write, and then in parentheses, and you got to have the quotations to tell it that it's a string. You could simply put, for example, H, and it would print an H, but if you want to put an entire string and not just one character, well, you need to have a way of processing that. That's the point of this subroutine up here, LCD puts. And this is actually one that comes from that string.h. But what it does is it references a pointer, str, and it will go through character by character and send that data 8 bits at a time to your LCD display. So it'll print an H, it'll go through your write routine and do that, then an E and do that. So that just allows you to type conveniently on one line in your program, hello world, instead of having to do write H, write E, write L, write L, write O, because you can imagine how much space that would actually take up. So this actually just tightens that up. Okay, we've got our PicKit 2 connected to our PicKit 2 demo board and our 8-bit LCD display. This is a 4x20 character display. Yeah, look at that mess of wires. That's disgusting. Spaghetti. I know, quick and dirty, but it should do the trick. So let's come over here to our MP lab and we'll hit load. Building, connecting to programmer. Come over here. It's programming. And does it work? Yes, it does. Hello world. You'll notice right here, this part is actually burned out. That's why I use this as kind of a test bed thing now, because it had actually failed like that at one point. So anyway, I wanted to show you that. Just quick little thing about LCD displays, show you how to initialize them, show you how to schematically connect them, show you how to program them so that you can add them to your next project. And they're really useful. As you can see, you can display text, you can display data. As I showed you in the beginning, I had my DC electronic load that I had designed and programmed, which showed temperature, it showed voltage, current. Actually, let me show you that again. Okay, here it is again. You can see I've got it set here to a constant current of 1 amp, and currently the heatsink temperature is 17 degrees Celsius. So what I'm going to do is go ahead and hit the load button here. Sorry, get my hand out of the way. There, it beeped. And you can see it's showing us right now, it's measuring 10.03 volts at 0.998 amps, which is calculated to be 10.01 watts and about 10 ohms. And you can see the data is actually changing there. That's the great thing about LCD character displays. It gives you constant, up-to-date information about a process that's going on. Things that you otherwise wouldn't be able to see or know. Yeah, sure, they have analog meters that can give you the same information. You can buy individual digital meters that'll show you similar information, but it's just not as satisfying, and it doesn't give you all that information in one place in a compact size. And I'll just show you here that we are in fact 10 volts, 1 amp there. There's a little bit of parallax there, so you're not seeing it exact, and the meters, they're analog, they're not 100% spot on. I definitely trust the load a lot more because this is a 16-bit analog to digital converter in there. So when that says 0.998, I believe it. When it says 10.3 volts, I believe that. And you can see that our heatsink temperature, since we're drawing a load of 10 watts, has gone up to 18 degrees C. The fans to cool the heat sinks don't come on until after 30 degrees C. Geez, we're crooked. That's better. Anyhow, just wanted to show you that about LCD character displays. I hope you will take on the challenge of Whoa, what did that just do there? I don't know, software bug maybe. I hope next time you take on the challenge of using a LCD character display in your next project. So if you have any questions, feel free to leave it in the comments. I try to answer things when I can. I hope that the community watching this video have things that they can add. I don't always get it 100% right. I just try to move things along in the general direction to inspire people to do things more complicated than they might have done in the past. Anyhow, like this video. Let me zoom out. Yeah, that's better. Hey, we've got monkey wrench and ham bones. Yeah, they are lab assistants. Click like if you haven't done so. Subscribe if you haven't done so. And follow me on Twitter at OhmsAtHome. I'll see you.